Okay, let's move on to Chapter 13, Section 5. This is tests concerning proportions. And this will boil down to two different scenarios for us. The first scenario will be when we're working with small samples, and the second scenario will be when we're working with large samples. So let's consider a test that concerns the parameter theta of the binomial distribution. Remember, for the binomial distribution, x is going to correspond to the number of successes in n trials, and b, y, n comma theta is going to be the probability of y successes in n trials. That's our probability distribution for the binomial distribution. And in this case, the theta is going to be the probability of success. So we're interested in testing the null hypothesis, where theta is equal to theta naught, versus, say, the alternative where theta is greater than theta naught. This will be our right-tailed alternative. In this case, we'll define the rejection region of size alpha to be the following. It's going to be the set of x values where x is greater than or equal to some k alpha, where this k alpha value is going to be the smallest integer, such that if we look at the sum where y goes from k alpha to n of those binomial probabilities, the sum of those probabilities has to be less than or equal to alpha. And here, when we're computing those probabilities, we'll be using theta equal to theta naught, which is our assumed value for theta under the null hypothesis. So again, this is just how we construct our rejection region for the right-tailed test. If instead we're trying to construct a rejection region for the left-tailed test, that will be the scenario where theta is claimed to be less than theta naught. We'll define a rejection region of size alpha as follows. It's going to be the set of x values where x is less than or equal to some k alpha prime, and in this case k alpha prime will be the largest integer, so that if we look at the sum from 0 to k alpha prime and we for those binomial probabilities, we'll get a sum that's less than or equal to alpha, and again, theta is given by theta naught under the null hypothesis. Versus our two-tailed rejection region, it's going to look like a combination of the two left and right-tailed rejection regions that we just constructed. This will be of size alpha, and it's given by the set of x values where x is either less than or equal to some k alpha over 2 prime, or x is greater than or equal to some k alpha over 2. So let's look at an example. We've got a doctor who claims that less than 30% of all persons exposed to a certain amount of radiation will feel ill effects. So suppose we have a random sample of 19 people exposed to this particular radiation, and only one of those 19 people ended up feeling any ill effects from the exposure. So what we want to do is at the 5% significance level is determine whether or not there's evidence to suggest that less than 30% of those exposed to this radiation will get ill. So we're testing this doctor's claim. So our hypotheses will be as follows. The null hypothesis would be that 30% are going to get sick versus the doctor's claim that less than 30% get sick for the alternative. And our critical region here, since this is a left-tailed test, will be the set of x values where x is less than or equal to some k alpha 0.05. Now, how do we identify this k alpha 0.05? It's going to be the largest integer, so that if we look at the sum of the binomial probabilities where y goes from 0 to this k value, the sum of those probabilities has to be less than or equal to alpha. In order to find this k value then, we're going to have to compute some binomial probabilities. So let's get started. If we're interested in the probability that, say, x is equal to 0, then that's going to be a 19 choose 0 times our probability of success, which is 0.3 to the 0 power, times our probability of failure, which is 0.7 to the 19 power. If we do that, we get 0.0011. All right, well that number is definitely less than our alpha of 0.05, so now we'll go and we'll compute the next binomial probability, the probability that x takes the value of 1. So that will be 19 choose 1 times 0.3 to the 1 power times 0.7 to the 18. If we do that, we get 0.0093. The sum of these two values is still less than 0.05. So now let's look at the next probability, the probability that x is equal to 2. This is 19 choose 2 times 0.3 to the 2 times 0.7 to the 17. If we do that, we get 0.0358. And if we look at the sum of those three values, that's still less than alpha. But if we move on to the next probability that x is equal to 3, that will be 0.0869. I'll spare you the details here. You can figure it out. And we see that if we were to add that probability into these three, then that would give us a value that's greater than alpha. As such, then our rejection region will be the set of x values where x is less than or equal to 2, because if we take the probability that x is less than or equal to 2, we'll add those three probabilities from before, the 0.0011 plus 0.0093 plus 0.0358, and we'll get 0.046, which is definitely less than 0.05. And x equal to 2 is the largest such integer where we look at those sum of probabilities and get something less than 0.05. Now, what's our test statistic here? Well, our test statistic x is just the number of successes. Since we have one success in 19, and that one success is less than or equal to 2, that tells us that our test statistic lies in the rejection region, so we're going to reject the null hypothesis in favor of claim that at the 5% significance level, there is sufficient evidence to suggest that less than 30% of those exposed to this particular radiation will get ill. At this stage, you might be thinking that that last approach, using our critical region, required an enormous amount of work because we had to add up all of those probabilities until we found something that was less than alpha. So let's revisit that same example, and we'll use the p-value approach instead and see how that one works. Here, again, our hypotheses, the null hypothesis is that theta is equal to 30% versus the alternative, which says theta is strictly less than 30%. We know our test statistic is x equal to 1. So when we go to compute a p-value, then our job, remember, is to find the probability of observing a test statistic as extreme or more extreme than what we observed. So as extreme would be getting a probability of x equal to 1. More extreme means less than 1. So in this case, the only other option, since this is a discrete probability distribution, is that we would also be looking at the probability that x equals 0. We've already computed those two probabilities in our previous example, so we can use those numbers, 0.0011 and 0.0093. If we add them together, that gives us 0.0104, which is our p-value. And again, since our value is less than our alpha value of 0.05, that gives us evidence to suggest that there is 30% of those exposed to this radiation that will end up getting sick. So we can see that maybe the p-value approach is a little bit faster in this case, but in the event that we have to do something like we need to add up more than just a couple probabilities, it's in our interest to either make use of binomial tables or to make use of the calculator so that we can do it more quickly, because our calculator can generate these probabilities for us. Now, what if we end up having a large sample, say n greater than or equal to 30, we certainly wouldn't want to use the method that we just used. It would be too cumbersome. But we might remember from before that for large samples, the binomial distribution may be approximated with the standard normal distribution. As such, we can have a large sample test for the binomial parameter theta, in which case we define our null hypothesis to be that theta is equal to some number theta naught, versus our alternatives, theta is either not equal to theta naught, it's less than, or it's greater than theta naught. So our typical two-tailed, left-tailed, and right-tailed options. But in this case, since we're going to approximate the binomial distribution with a normal distribution, then our test statistic is a z-score, and so our rejection regions will then be based upon the z-distribution. So you'll recognize these as the same form of rejection regions that we had previously. For the two-tailed test, we're looking at z-scores whose absolute value are greater than or equal to the z-alpha over 2. For the left-tailed test, we're looking at z-values less than or equal to some critical value, negative z-alpha, and for the right-tailed test, our critical value will be the positive z-alpha. And our test statistic in this case will be a z-score that we compute by doing x minus n times theta naught. Remember what that's doing here is it's looking at our numbers of successes and comparing it to what we would have expected to get under the null hypothesis, n times theta naught, and we'll divide by the estimate for our standard error, which we'll find by doing the square root of n times theta naught times 1 minus theta naught. Moving on to our last example, let's look at a random sample of 600 cars that make a right turn at a certain intersection, and suppose 157 of those 600 pulled into the wrong lane, and we want to use the 5% level of significance to determine if the actual proportion of drivers who make this mistake at the given intersection differs from 30%. Our hypotheses will be defined as follows. For the null hypothesis, that will state that the proportion of drivers who make this mistake is 30%, whereas the alternative would say that the proportion is not equal to 30%. Our critical region, which will depend upon a z-distribution, will be the set of z-values where we're taking our area, which is alpha of 0.05, dividing it in 2 to get a 0.025. So we're looking for a z-score for our critical value with an area of 0.025 in the right tail. If we look that up in our table, it's 1.96. So our rejection region is the set of z-values where if we look at their absolute value, we'll get something greater than or equal to 1.96. And then we use our formula to compute our test statistic. We do 157 minus 600 times the 0.3. Remember, the 600 times the 0.3 is going to give us what we would have expected for the number of cars to make the wrong turn given our assumption of the null hypothesis that 30% do so. And then we'll divide by our estimate for standard error, and we get a test statistic of negative 2.049. We can see that does lie in the rejection region because its absolute value is greater than 1.96. So that tells us that at the 5% significance level, there is sufficient evidence to suggest that the actual proportion of drivers who make this mistake at a given intersection differs from 30%. That completes our discussion now for the test concerning variances and the test concerning proportions. Next time when you come back, we'll be moving on to a new topic which deals with some tests relating to questions about categorical variables. Everything we've done so far deals with numerical variables, so we'll have a different approach that we'll work with. Thank you.